Okay, everybody, let's wrap up with wind. Okay, so one of the last things we need to deal with is wind speed. And the speed of the wind depends on the difference in air pressure between two locations. Difference in air pressure. And this is what's called pressure gradient, or pressure gradient force. And that's really the, again, difference in air pressure between 2 points. So we're back to gradient again, and we can calculate pressure gradient the same way you would calculate the gradient of slope or temperature gradient, anything like that. So as the pressure gradient increases, so does wind speed. Okay, so as the pressure gradient gets larger, wind speed increases. This is a direct relationship, meaning our line graph would look like that. Pressure gradient's increasing, wind speed goes up. Now, this is a concept we've talked about a little bit informally, but if we look at a weather map and we have isobars, and again we can see 4 millibar differences. Okay, 1004, 1008, there's 1000, 1012, 1016. 4 millibar interval is considered standard. And when we look at a weather map like this, we could tell where the pressure gradient is greatest just by looking at the lines. Okay, where the lines are closest together near the city Holland, that's where the pressure gradient would be greatest on this weather map. This city is between these two lines. The lines are closest together there. Where the lines are close together, pressure gradient is greatest, which means we have the strongest winds near that location as well. And that was something that we talked about once, a couple of times maybe, when looking at daily weather maps. Now, the last thing regarding wind specifically is global wind patterns. And if we start out with a simplified, non-rotating Earth, just to make it simple, and we'll add rotation in a minute, but this is a very simplified diagram. It's just to get the idea across. In reality, the global wind patterns are much more complex. So we have surface winds that you would feel when you go outside, but there are regular global wind patterns that you might not feel at the surface but happen higher up in the atmosphere. These global wind patterns, you might be familiar with the trade winds, for instance. You learn about those in social studies oftentimes. They're a global wind. There's many other global winds as well. But if we simplify the process, we have our equator, and we know that it's hot here. So we're going to have hot air rising up at the equator. And then as it cools, it's going to sink and it's going to move towards the poles. It's going to get cold, and it's going to head back towards the equator again. And this is this convection cycle that we've talked about many times. And again, we see this in the outer core of the Earth. We see it in oceans. We see it even in the classroom where we have a heat source. Hot air rises, or it could be hot water or even magma. In this case, though, it's obviously air. Hot air rises, it cools, it sinks, and the process repeats. Now, for the actual Earth, it's a little more complex than this, but this is the basic idea, and then we need to add a couple of things to it. For example, rotation. Okay, when we add rotation, that changes the pattern a little bit. if we divide the Earth up into the equator, 30 north, 30 south, 60 north, and the poles, because of the Coriolis effect, and we'll look at the Coriolis effect in more detail, we actually have a more complex pattern than in the non-rotating model. So if we start out at our equator, we still have hot air rising. So the hot air rises, but in reality, it can't make it all the way to the poles. It's going to cool off and sink before it gets to the poles. So it's going to start to cool down, this hot air, and it's going to move across, but it's going to sink at about 30 degrees north. It's going to come down, and it's going to sink at 30 degrees south. So we have hot air here, then it cools. It's going to cool here, and it starts to sink at 30 degrees north and 30 degrees south. Okay, then if we continue with this, it's going to go back towards the equator. But this convection cell is not only happening just on the left side of the planet, but on the right side and all along. Remember, it's a three-dimensional Earth, so we have basically like a belt of convection cell going around the equator. But it continues to get a little more complex. We would then have the pattern continue, and now we're going to have air rise at 60 degrees south. So air is going to rise there. It's going to go back like this, and the pattern's going to continue. Air is going to sink at the poles and go back. And then we're going to have the same thing happen up here. Air is going to rise at 60 degrees north. It's going to sink towards the poles and return. Now, this is still a simplified version of what's going on, because now we actually have to include the deflection of the wind due to Coriolis effect. So, if we pretend that we're at the North Pole and we're looking down towards 60 degrees, the wind is coming down from the pole to 60, and if you imagine you're facing this arrowhead, you're at the pole looking down, your right is going to be, well, let me draw it this way. If the arrow is coming down, we've got our wind going from the pole to 60, and again, we're facing the 60, my right is going to be this way, and the wind is going to get deflected this way. So now our wind curves like that. From 30 degrees to 60 degrees north, the wind is moving up or north, and now my right is to this side, and now the wind curves like this. And then for 30 to 0, it's going to be curving like this again. Again, if you're confused by this, remember it always goes to the right in the northern hemisphere. And the reason it's not the same everywhere is because the wind is coming from different directions. So it is always getting deflected to the right. But here from 30 to 0, right is going to be these curves going this way. From 30 to 60, if the wind is moving in a north direction, the wind is going to be curving to the right like this. And then here now, the wind is going from the north to the south, so it's going to be opposite. In the southern hemisphere, now we have wind being deflected to the left. So my wind in this case is going from 30 to 0, and it's going to get deflected to the left, and we're going to have something kind of like this happen. And then the opposite down here in 30 to 60. And then our high would be something like that. Okay. This diagram is in your reference table. I, off the top of my head, don't remember what page, but it's definitely in there. So you might want to get your reference table out, try to find that. But it's definitely in there somewhere. So you might want to take a look for that. We'll go into this in more detail But remember, when air is rising, it's cooling. And cooling air forms clouds. And that's why at the equator we have lots of clouds, and that's where the world's rainforests are. And we see the same thing at 60 degrees north. We have lots of clouds. Think about the city of Seattle. It's known for its cloudiness and lots of rain. At 60 degrees south, you're going to have lots of clouds here too. Where the air is sinking, it's getting warm, which is happening at 30 degrees north and south. The air is warming as it's sinking. It's getting closer to the surface. It's getting warmer. And warmer air evaporates moisture instead of condenses it. So instead of cloud development, we have the opposite. We have high pressure. You're going to have high pressure here as well, which means that at 30 degrees north and south, you're going to have good sunny weather all the time. And if you think about a climate like that, hopefully what comes to mind is a desert. And at 30 degrees north and 30 degrees south, this is where the world's largest deserts are. The Sahara, the Malakari, or the Kalahari rather, all of these famous deserts that you might have heard of, parts of the Middle East, Iran, Iraq, places like that. 30 degrees, really, really hot, dry locations, desert environments occur at 30 degrees south and north. You get lots of rain at 60 degrees north and south, and certainly lots of rain at the equator. And this is why. It's the difference between rising air and sinking air. Where we have rising air, you're going to get rain. Where you have sinking air, you're going to have essentially a desert. Okay, Death Valley is at about 30 degrees north, one of the driest, hottest places on the planet. Okay, the Atacama Desert in Chile, one of the driest places on the planet. That desert is so dry, it's gone years without a single drop of rain. So this is where the most extreme desert environments would be. And then in the 60s, south and north, and at 0 are where we find the moistest locations on the planet. And we're kind of in between. We're at about 45 or 41 degrees. So we're in between. We get a lot of rain, but we also have dry spells too. We're kind of in between on that. Okay, that's it for wind. And next up is air masses and fronts.